Hello everyone. Today we will discuss about domain name system, that is DNS, the concepts, structure, resolution and security of DNS. Need for DNS. To identify an entity, TCP/IP protocols use the IP address, which uniquely identifies the connection of a host to the internet. However, as humans, we prefer to use names instead of numeric addresses. Therefore, the internet needs to have a directory system that can map a name to an address. Since the internet is so huge today, a central directory system cannot hold all the mappings. In addition, if the central computer fails, the whole communication network will collapse. A better solution is to distribute the information among many computers in the world. In this method, the host that needs mapping can contact the closest computer holding the needed information. This method is used by the domain name system, that is our DNS. Now, coming to the purpose of DNS. The following figure shows how TCP/IP uses a DNS client and a DNS server to map a name to an address. A user wants to use a file transfer client to access the corresponding file transfer server running on a remote host. The user knows only the file transfer server name. However, the TCP/IP suite needs the IP address of the file transfer server to make the connection. Here, the following 6 steps will map the host name to an address. The following 6 steps will describe that. First one, the user passes the host name to the file transfer client. Second step, the file transfer client passes the host name to the DNS client. Coming to the third step, each computer, after being booted, knows the address of one DNS server. The DNS client sends a message to a DNS server with a query that gives the file transfer server name using the known IP address of the DNS server. Moving to the fourth step, the DNS server responds with the IP address of the desired file transfer server. Fifth step, the DNS server passes the IP address to the file transfer client. Last but not the least, the file transfer client now uses the received IP address to access the file transfer server. Coming to the namespace. A namespace that maps each address to a unique name can be organized in two ways. They are flat or hierarchical namespace. In a flat namespace, a name is assigned to an address. A name in this space is a sequence of characters without any structure. The names may or may not have a common section. If they do, it has no meaning. But the main disadvantage of a flat namespace is that it cannot be used in a large system such as the internet because it must be centrally controlled to avoid ambiguity and duplication. If you consider hierarchical namespace, in a hierarchical namespace, each name is made of several parts. The first part can define the nature of the organization. The second part can define the name of an organization. The third part can define departments in the organization and so on. In this case, the authority to assign and control the name spaces can be decentralized. A central authority can assign the part of the name that defines the nature of the organization and name of the organization, whereas the responsibility for the rest of the name can be given to the organization itself. The organization can add suffixes to the name to define its host or resources. The management of the organization need not worry that the prefix chosen for a host is taken by another organization, because even if a part of an address is the same, the whole address is different. Coming to the structure of domain namespace, to have a hierarchical namespace, a domain namespace was designed. In this design, the names are defined in an inverted tree structure with the root at the top. The tree can have only 128 levels. Level 0 is the root to level 127. Here, domain names and labels are shown. Usually, label in the sense each node in the tree has a label, which is a string with a maximum of 63 characters. The root label is a null string or it is an empty string, whereas DNS requires that children of a node, that is nothing but nodes that branch from the same node, have different labels, which guarantees the uniqueness of the domain names. Coming to the domain name, each node in the tree has a domain name. A full domain name is a sequence of labels separated by dots. The domain names are always read from the node up to the root. The last label is the label of the root, that is null. This means that a full domain name always ends in a null label, which means the last character is a dot because the null string is nothing. Suppose if a label is terminated by a null string, it is called a fully qualified domain name, FQDN. The name must end with a null label, but because null means nothing, the label ends with a dot. If a label is not terminated by a null string, it is called a partially qualified domain name, that is PQDN. PQDN starts from a node, but it does not reach the root. It is used when the name to be resolved belongs to the same site as the client. Here, the resolver can supply the missing part called the suffix to create an fully qualified domain name, that is FQDN. Coming to the domains. A domain is a subtree of the domain namespace. The name of the domain is the name of the node at the top of the subtree. Here we can see the domains. Note that a domain may itself be divided into other domains. The information contained in the domain namespace must be stored. However, it is very inefficient and also not reliable to have just one computer store such a huge amount of information. It is inefficient because responding to requests from all over the world places a heavy load on the system. It is not reliable because any failure makes the data inaccessible. Coming to the hierarchy of name servers. This particular figure shows the hierarchy of name servers. The problem what we just addressed, the problem what I just stated, to that we have to find a solution through this. The solution to these problems is to distribute the information among many computers. We call those computers as DNS servers. One way to do this is to divide the whole space into many domains based on the first level. In other words, we let the root stand alone and create as many subtrees as there are first level nodes. Because a domain created this way could be very large, and DNS allows domains to be divided further into smaller subdomains. Each server can be responsible or authoritative for either a large or smaller domain. We can also state it as if we have a hierarchy of servers in the same way that we have a hierarchy of names. So here in hierarchy of name servers are shown. Next we have zones. In this figure, zone is shown. Since the complete domain name hierarchy cannot be stored on a single server, it is divided among many servers. What a server is responsible for or has authority over is called a zone. We can define a zone as contiguous part of the entire tree. If a server accepts responsibility for a domain and does not divide the domain into smaller domains, the domain and the zone refer to the same thing. But the server makes a database called a zone file and keeps all the information for every node under that domain. However, if a server divides its domain into subdomains and delegates part of its authority to other servers, domain and zone refer to different things. The information about the nodes in the subdomains is stored in the servers at the lower levels, with the original server keeping some sort of reference to these lower level servers. Now, coming to the root server. A root server is a server whose zone consists of the whole tree. A root server usually does not store any information about domains but delegates its authority to other servers, keeping references to those servers. There are several root servers, each covering the whole domain namespace. The root servers are distributed all around the world. Coming to primary and secondary servers. DNS defines two types of servers. We can call them as primary server and secondary server. Coming to primary server, a primary server is a server that stores a file about the zone for which it is an authority. It is responsible for creating, maintaining, and updating the zone file. It stores the zone file on a local disk. Coming to the secondary server, it is a server that transfers the complete information about a zone from another server, that is primary or secondary server, and stores the file on its local disk. The secondary server neither creates nor updates the zone files. If updating is required, it must be done by the primary server only, which sends the updated version to the secondary server. Whereas the primary and secondary servers are both authoritative for the zones they serve. The idea is not to put the secondary server at a lower level of authority, but to create redundancy for the data so that if one server fails, the other can continue serving clients. Server can be a primary server for a specific zone and a secondary server for another zone. Therefore, usually, when we refer to a server as a primary or a secondary server, we should be careful about which zone we refer to because the role will change from zone to zone. Coming to the next topic, that is DNS in Internet. DNS is a protocol that can be used in different platforms. In the Internet, the DNS or domain name space or tree was originally divided into three different sections. We call them as generic domains, country domains, and the inverse domains. However, due to the rapid growth of the internet, it became extremely difficult to keep track of the inverse domains, which could be used to find the name of a host when given the IP address. The inverse domains are now deprecated, so we will focus only on the first two. They are generic domains and country domains. This figure shows the generic domain structure. The generic domains define registered hosts according to their generic behavior. Each node in the tree defines a domain, which is an index to the domain namespace database. Looking at the tree, we see that the first level in the generic domain section allows 14 possible labels. If you want to see the list of all these 14 labels, it is given in the textbook, table 26.12. There, certain labels and their particular descriptions are given, such as if the label is INT, it stands for International Organization. If the label is MIL, it is military group. If the label is museum, it is related to museum. If the label is COM, it is commercial organizations, and so on. Coming to the next type of domain, that is country domains. The country domain section uses two character country abbreviations. Example, US for United States. Second labels can be organizational or they can be more specific national designations. If you consider United States, for example, it uses state abbreviations as a subdivision of US. For example, CA.US, like that. So here if you see, it shows the country domains section. The address uci.ca.us can be translated to University of California, Irvine in the state of California in the United States. Coming to the next topic, that is DNS resolution methods. Mapping a name to an address is called name address resolution. DNS is designed as a client server application, a host that needs to map an address to a name or a name to an address calls a DNS client and a resolver. This resolver accesses the closest DNS server with a mapping request. If the server has the information, it satisfies the resolver. Otherwise, it either refers the resolver to other servers or asks other servers to provide the information. After the resolver receives the mapping, it interprets the response to see if it is a real resolution or just an error. And finally, delivers the result to the process that requested it. Here, a resolution can be either recursive or iterative. Coming to the first type, that is recursive resolution. Figure shows a simple example of recursive resolution. We assume that an application program running on a host named some.anet.com needs to find the IP address of another host named engineering.macrohill.com. The example same is quoted in the textbook, so I am taking that same example. So this engineering.macrohill.com to send a message to. So the source host is connected to the ANET internet service provider. The destination host is connected to the McGraw-Hill network. The application program on the source host calls the DNS resolver, that is client, to find the IP address of the destination host. The resolver, which does not know this address, sends the query to the local DNS server. That is in this case, it is dns.anet.com running at the ANET ISP site. Now, we assume that this server does not know the IP address of the destination host either. It sends the query to a root DNS server whose IP address is supposed to be known to this local DNS server. Now, root servers do not normally keep the mapping between names and IP addresses, but a root server should at least know about one server at each top level domain. In this case, a server is responsible for COM domain. The query is sent to this top level domain server. We assume that this server does not know the name address mapping of this specific destination, but it knows the IP address of the local DNS server in the McGraw-Hill company, that is dns.mcgrawhill.com. The query is sent to this server. I hope you are pointing out the event with that of the numbers of the event that is given there. Now I am focusing about event 4, which knows the IP address of the destination host. The IP address is now sent back to the top level DNS server, which corresponds to event 5, then back to the root server, which corresponds to event 6, then back to the ISP DNS server, which may cache it for the future queries. Now we are in event 7. And finally, back to the source host, that is event 8. So here, if you go for identifying the event, the first event is that the resolver, which does not know this address, sends the query to the local DNS server running at the ANET site. And the next is that uh, we assume that the server does not know the IP address of the destination host. So it sends the query to a root DNS server whose IP address is supposed to be known to this local DNS server. So event 2 is done. And similarly, root servers do not, as we know, normally keep the chain mapping between names and IP address, but a root server should at least know about one server at each top level domain. So here the query is sent to this top level domain server. So event 3 is done. Now we assume that the server does not know the name address mapping of this specific destination, but it knows the IP address of the local DNS server in the McGraw-Hill company. So the query is sent to this server. Here event 4 is completed, which knows the IP address of the destination host. Now the IP address is now sent back to the top level DNS server. Here the event 5 is done, then back to the root server, event 6 is done, then back to the ISP DNS server, which may cache it for the future queries by completing event 7, and finally back to the source host by completing the last event, that is event 8. This is about first resolution, that is recursive resolution. Now, coming to the iterative resolution. Here also, in iterative resolution, each server that does not know the mapping sends the IP address of the next server back to the one that requested it. So, in this figure, the flow of the information in an iterative resolution in the same scenario as the one depicted before is shown. Normally, the iterative resolution takes place between two local servers. The original resolver gets the final answer from the local server. But here we have to note that the messages shown by events 2, 4 and 6 contains the same query. But the message shown by event 3 contains the IP address of the top level domain server. The message shown by event 5 contains the IP address of the McGraw-Hill local DNS server, and the message shown by event 7 contains the IP address of the destination. So at the end, when the ANET local DNS server receives the IP address of the destination, it sends it to the resolver by ending event 8. I hope you have understood the differences between iterative as well as recursive resolution. Now, moving to the next topic, that is DNS caching. Each time a server receives a query for a name that is not in its domain, it needs to search its database for a particular server IP address. Reduction of this search time would obviously increase the efficiency. So, the DNS handles this with a mechanism that can be called as caching. Here, when a server asks for a mapping from another server and receives the response, it stores this particular information in its cache memory before sending that to the client. If the same or another client asks for the same mapping information, it can check its cache memory and resolve the problem. However, to inform the client that the response is coming from the cache memory and not from an authoritative source, the server makes the response as unauthoritative. Caching will obviously speeds up resolution, but it can also be problematic in some situation. Suppose if a server caches a mapping for a long time, it may send an outdated mapping to the client. To counter this, two techniques will be used. First one is that the authoritative server always adds information to the mapping called time to live or TTL. This will define the time in seconds that the receiving server can cache the information. After that particular time, the mapping is invalid and any query must be sent again to the authoritative server. Second, DNS servers that each server keep a TTL counter for each mapping it caches. The cache memory must be searched periodically and those mappings with an expired TTL must be purged. Resource records. We studied about zones. The zone information associated with the server is implemented as a set of resource records. In other words, a name server stores a database of resource records. A resource records is a 5 tuple structure. 5 tuple structure in the sense domain name will be there, second is type, and third one is class, fourth one is TTL, and the last one is value. The domain name field is what identifies the resource record. The value defines the information kept about the domain name. The TTL defines the number of seconds for which the information is valid. The class defines the type of the network. And here we are only interested in the class IN because it stands for internet. And the type defines how the value should be interpreted. And in the textbook, if you refer, there is a table called 26.13 where the type as well as interpretation of that value is given. A in the sense a 32-bit IPv4 address. Similarly, as it is shown, AAAA means an IPv6 address. CNAME means it defines an alias for the official name of a host. MX stands for redirects mail to a mail server. NS stands for identifies the authoritative servers for a zone, whereas the role of SOA is to mark the beginning of a zone. Now, coming to the next topic, that is DNS message. To retrieve information about host, DNS use two types of messages. One is query and one more is response. Both type of these messages will have the same format. The format is shown here. This is the DNS message format. Here, the first field, that is identification field, is used by the client to match the response with the query. Next, we have flags. This flag field defines whether the message is a query or whether it is a response. And it also includes status of error. The next four fields in the header defines the number of each record type in the message. Next, we have the question section. It consists of one or more question records. It is present in both query as well as response messages. Next, we have answer section. It consists of one or more resource records. It is present only in the response messages. Now, next comes authoritative section. It gives information about one or more authoritative servers for the query. Last one is the additional information section. It provides additional information that may help the resolver. The next concept is encapsulation. DNS can use either UDP or TCP, but in both the cases, the well-known port used by the server is port 53. UDP is used when the size of the response message is less than 512 bytes because most of the UDP packages have a 512 byte packet size limit. If the size of the response message is greater than 512 bytes, obviously a TCP connection is used. But in that case, two situations can occur. First one, if the resolver has prior knowledge that the size of the response message is more than 512 bytes, it uses the TCP connection. And for example, if a secondary name server that acts as a client needs a zone transfer from a primary server, it uses the TCP connection because the size of the information being transferred usually exceeds 512 bytes. Now, if the second case, if the resolver does not know the size of the response message, it can use the UDP port. However, if the size of the response message is greater than 512 bytes, the server truncates the message and turns on the TC bit. The resolver now opens a TCP connection and repeats the request to get a full response from the server. This is about encapsulation. Next topic is registrars. Now I have a question. How are new domains added to our DNS? The answer is it is via registrar. Registrar is a commercial entity accredited by ICANN. Our registrar first verifies that the requested domain name is unique and then enters it into the DNS database. Obviously, a fee is charged. Today, there are many different registrars available. Their names, address, everything you can get it in the internet. To register, the organization needs to give the name of its server and the IP address of the server. This is about registrars. Next is dynamic DNS or DDNS. When the DNS was designed, no one predicted that there would be so many address changes. In DNS, when there is a change, such as adding a new host or removing an existing host or changing the IP address, the change must be made to an DNS master file. These types of changes involve obviously a lot of manual updating. But we know the size of today's internet is very large, and the size of today's internet does not allow for this kind of manual operation. So the DNS master file must be updated dynamically. The Dynamic Domain Name System DDNS therefore was devised to respond to this need. In DDNS, when a binding between a name and an address is determined, the information is sent usually by DHCP to a primary DNS server. About DHCP, we have studied in detail. The primary server updates the zone. The secondary servers are notified either actively or passively. In active notification, the primary server sends a message to the secondary servers about the change in the zone. Whereas in passive notification, the secondary servers periodically check for any changes. In both the cases, after being notified about the change, the secondary servers request information about the entire zone. This is called as zone transfer. To provide security and to prevent unauthorized changes in the DNS records, DDNS can use an authentication mechanism. So, from this, we are moving to the very important topic, that is DNS security. As we know, DNS is one of the most important systems in the internet infrastructure. It provides crucial services to internet users. Applications such as web access or email are heavily dependent on the proper operation of DNS. DNS can be attacked in several ways. First one, DNS. uh, To attack DNS, the attacker may read the response of a DNS server to find the nature or names of sites the user mostly accesses. This type of information can be used to find the user's profile. To prevent this attack, DNS messages need to be confidential. Second way, the attacker may intercept the response of a DNS server and change it or create a totally new bogus response to direct the user to the site or domain the attacker wishes the user to access. This type of attack can be prevented using message origin authentication and message integrity. Coming to the third type, the attacker may flood the DNS server to overwhelm it or eventually crash it. This type of attack can be prevented using the provision against denial of service attack. But to protect DNS, IETF has devised a technology named DNS security, that is DNSSEC, that will provide message origin authentication and message integrity using a security service called digital signature. DNSSEC does not provide confidentiality for the DNS messages. There is no specific protection against the denial of service attack in the specification of DNSSEC. But the caching system protects the upper level servers against this attack to some extent. Thank you.